Okay, welcome back to another video in our statics class. We are looking at frame analysis. And in the previous video, we had started this example 5.3 problem from the textbook. And the first thing we did was find all of the reaction forces. So by summing the moments about point A, we were able to find the horizontal reaction at B, which was 11,070. Now, the textbook author likes to use H and V for horizontal and vertical. I tend to use X and Y, but same idea there, same concept. And so the horizontal reaction at A has to cancel out with that horizontal reaction at B, so that's also 1170. And then we summed all the vertical forces acting down on this truss, and those are all reacted by the vertical force at support A, which was 13,800. So once we have those reaction forces found, we can now begin the frame analysis. And the way we do that is by looking at individual frame members. So this slide here is maybe a little unnecessary. This is kind of giving us an overall look at the different frame members and the way the three joints, because if I back up here, we have a pinned joint at C, D, and E. And you have to remember that when we're doing our frame analysis, that's all we're trying to do is figure out what these forces are at C, D, and E. How is this joint affecting the post? How is it affecting the boom? The joint at D, how is that affecting the boom, and how is it affecting the brace? And so on and so forth. All of these joints will have either vertical, horizontal, or a combination of both horizontal and vertical reactions pushing or pulling against these three frame members. So this is kind of an overall look and guess at what is going on here in terms of the pushing and pulling. But let's get past this and just jump into our first free body diagram. And there is a little bit of trial and error here in terms of deciding which frame member is the best to start with. And there is not necessarily a right or wrong answer. If I back up again, I don't think I would want to choose the brace to start off with. The joint here is going to have vertical and horizontal reaction forces. I don't really know either of them. The only thing I know about the brace is that it has a 900-pound weight coming down, but that would leave 4 other unknown forces. Probably wouldn't want to start there. The post, it's going to have potentially a vertical and horizontal reaction at C, potentially vertical and horizontal at E. I do know the reaction forces at A and the reaction at B. So that still is going to I'm not going to be able to solve all of the unknown forces there right off the bat. But the post, I could see us starting at the post. That could be a reasonable starting point. And then we have the horizontal boom here, which, as you saw, is the framing member that the textbook chooses to start with. Is it the only option as far as starting? I don't think. I think we could have maybe started with the post as well, but it's kind of a toss-up, so we'll just go with the horizontal boom. Let's go with it. So what we need to do when we do a frame analysis is isolate that one structural member, the boom, that one horizontal member that was 14 feet long, and draw a free body diagram of it, which is what we have here. And we need to label all of the forces. We had a 10,000-pound externally applied force. Then we have the reaction forces, the pin. Remember this joint D, this is a pin. And a pin connection has two reaction forces, vertical and horizontal. So it makes sense to assume that the vertical reaction here is going up. Remember, we've got this giant load here at the end trying to pull this whole boom, pull the end of it down. So it makes sense to assume that that's going to want to push it back up. Also, this is going to cause rotation about point C, this big load out here at the end. So it's sort of going to cause rotation in this clockwise direction. It makes sense also that D is going to be kind of pushing back, that that diagonal framing member was in compression. So it's pushing both up and to the right. So the pin here at D is going to be pushing against the boom up and to the right. And that is how we need to think about it. How is the pin affecting the framing member? So it's pushing it up, it's pushing it to the right. Then we have the self-weight of the boom, which we were given as 1,500 pounds, and we are going to treat that as an individual point load that acts at the midpoint of the framing member. So if it's 14 feet long, that's 7 feet. Oh, look, it's already written there. I guess I didn't need to do that. And then we have the pin reaction forces at C. So you can almost think of this horizontal beam or boom, as it's called, almost like a teeter-totter. We've got this support here at DV that's holding it up. We've got this big load at the right pulling it down. The whole thing is going to flip up unless there's a reaction force over here at CV pulling it back down. So that's, I think, the reason why we can kind of assume that that force is going down. And because the horizontal force here at D was pushing the whole thing to the right, something has to react against that. So we're going to assume that joint C is pulling the boom to the left. Okay, so here we have all of our forces and their assumed directions. Now, what happens, you may be thinking, if you guess at one of these directions incorrectly? That's okay. These are just guesses at this point, and our analysis will either confirm that we were correct or show us that we were not correct. And so it all has to come down to whether the answers we get are positive or negative. So if we set up an equilibrium equation and solve it and we get a negative answer, the number was correct, it just means that the direction was wrong. So maybe if we solve for CV here and we get a negative value from our equation, it just means that actually this joint isn't pulling the boom down, it's pushing it up. So guessing at the direction at the beginning can help, but if you get it wrong, it's no big deal. It is just a guess. Okay, so how can we go about finding some of these unknown forces? Well, we have three equilibrium equations. We know that the sum of forces in the x direction equals 0. We know the sum of forces in the y direction equals 0. And we know that the sum of moments about any point will also equal 0. These are the three equilibrium formulas that we can apply to any free body diagram in order to help us find any missing forces. So let's start off in the horizontal reaction. CH is pulling to the left, DH is pulling to the right. So we could write out the sum of forces in the x direction equals 0, and that equals negative C. I guess I'll use H and V like the author does here to be consistent, although if I were doing this problem on my own, I'd be using X and Y. But okay, negative CH horizontally to the left plus DH to the right. Now, we don't know what CH is, and we don't know what DH is either, but we know that they cancel each other out, and they equal 0. So in other words, we can say CH equals DH in terms of their magnitude, equal to each other. but we don't know what either of them are, and that's okay. With frame analysis, we don't always get all of the answers right away. Sometimes we have to circle back a little later on. So we'll just make a little note that those two things are equal to each other, and we'll remember that and come back to it at a later point. So let's look at vertical reactions, or rather, let's find some vertical reactions by summing moments. So in the vertical reaction, we have CV, that's an unknown. We have DV, that's an unknown. And that's it. We know the other two vertical forces here. So I only have the two unknown vertical forces. That means if I were to sum the moments about one of these points, for instance, sum the moments about C, that takes CV out of the equation. CV does not cause a moment because it actually passes through joint C if we sum the moments about C. So that would leave just one unknown. So I'm going to sum the moments about C. Now I could also do this by summing the moments about D. If I sum the moments about D, that takes the vertical force dV out of the equation, and then that just leaves one unknown that I can solve for. But I'm going to do it at C. So the sum of moments about C is equal to 0. Let's write down what all of the moments about CV are. Okay, so CH passes through C horizontally, does not cause a moment. CV passes through the same point, does not cause a moment, so we can ignore those two. As we work our way across the beam or boom left to right, we have this 1,500 pound force. Okay, that is going to cause a moment. It has a moment arm distance of 7 feet. So 1,500 times 7. And that's going to come down and around in a clockwise direction. We consider that to be negative. Then the next force I come to, dV. dV is going to go up and around in a counterclockwise direction. So that's positive. dV times its moment arm distance of 10. dH, the horizontal force, passes right through joint C, so it doesn't cause a moment, so we can ignore that. But then we've got this big old 10,000 pound force out here at the end that causes positive rotation. Okay, so that's, well, clockwise rotation, I should say, which is actually negative. Negative 10,000. And its moment arm distance is 10 plus 4, 14 feet. Okay, so we just have the one unknown force here that we can solve for now. So dV equals 1,500 times 7 plus 10,000 times 14, and then divide all that by 10. Let's see what that's equal to. That gave me 15,050 pounds. Okay, and so what other forces do we need to solve here? So again, we've said CH is equal to DH. That's as far as we can go right now. We know they're equal to each other. We don't know what their magnitudes are. We found dV. That really only leaves CV as the last remaining force that we can potentially solve for. And we can. We can solve for these forces, for this force, by looking at all the forces in the y direction. So if I sum the forces in the y direction, it will equal 0. That's going to include CV going down, so negative CV, negative 1,500, positive dV, which was 15,050, so plus 1,550, and then minus 10,000. Okay, so that means